It's Dr. White's Fun with Graphs. This time we are going to talk about graph coloring, which is where we assign colors to the vertices such that every endpoint gets distinct colors. So the goal in graph coloring is to color the vertices so that endpoints of edges get distinct colors. So if you have an edge and one vertex is colored red, the other has to be colored something else. But we are okay if there is no edge between two vertices if they get the same color. So we don't want this situation. This is called a monochromatic edge. It's where both vertices get the same color. And we want to find a coloring that uses the minimum number possible of colors. So if you can color with fewer colors, that's great. And we let chi of g be this minimum number. And we will see that, in fact, chi of g always exists. At the very least, you could always color every vertex with a distinct color, so chi of g is at most the number of vertices. And this is usually one of the biggest problems in graph theory, is to determine the chromatic number of a graph. It has lots of real-world applications when the graph comes from a real-world network. For instance, suppose we've got the following graph. These vertices represent different committees that have to meet, and edges represent committees that have a member in common. And so, of course, if you're in two different committees, those two committees can't meet at the exact same time because you can't split your body in half. And so if you want to schedule meeting times, that would be a notion of a coloring. So it's worth pointing out colors aren't, when we say graph coloring, we don't always color with actual colors. They could be numbers, they could be times. And so in this case, it'd be times. You want to pick different times. And the point is, you want to make sure that the edges get distinct endpoints, because that means the committees are meeting at different times because they have a member in common. And so let's try to color this one. Let's just pick some vertex at random to color. So let's color that red. And I'm going to use circles for my colors. And then since this vertex is adjacent to this edge, it can't be colored red. So let's pick a different color, say blue. Now since this vertex is adjacent to a red vertex and a blue vertex, it can't be colored red or blue. So let's try green. And then let's keep going. Let's see here. This vertex is adjacent to a blue vertex and a green vertex. So we can use red here now because it's not adjacent to a red vertex, so let's just use red. And this fourth vertex is adjacent to a red, green, and a blue, so it can't be colored red, green, or blue. And so it turns out it looks like we need a fourth color. So let's color it yellow. And finally, the last vertex is adjacent to a red vertex and a yellow vertex, so let's color it with blue. And so this is an example of a coloring. It looks like we need 4 different meeting times. And so for right now, the best we can say is that the chromatic number is at most 4 because we found a 4 coloring. But one challenge is to determine whether or not we could have done better. After all, we just chose a certain approach to doing the coloring. It could be a different approach, could have gotten a different coloring. It might have been better to make different choices. And so we see it happens with committee scheduling. It's also used in course scheduling. You've got a bunch of courses at different times. The chromatic number in that, and you have so the vertices are courses, edges represent courses that are being taught at the same time or at overlapping times. Then the chromatic number would be the minimum number of classrooms you need to actually get your courses to fit. Pops up in taxi cab scheduling, job scheduling, and lots of other applications. And so as you could tell, classroom space is limited, and so there's a reason why this is the number we want to minimize. And so can we prove that you can't color this better? Well, you see these 4 vertices are all connected to each other. And so we see that whichever vertex we color first gets one color, the next vertex has to get something distinct, The third vertex has to get something distinct from the first two, and the fourth one has to get a color that's distinct from the other three. And so we see that in this case, 4 is also lower bound, and so 4 is the chromatic number. We need at least 4 meeting times, and we can't do it in less. And I'll point out, of course, that computing this number in general is very hard, given actually proving whether or not the chromatic number is at most 3. In other words, proving that a graph has a 3 coloring for a given graph. Finding a 3 coloring is $1 million problem. It's another one of those NP complete problems. If you could do it quickly, then you'd be a millionaire. However, there's certain cases we do know. Determining whether or not the chromatic number is at most 2 is actually very easy, because what does it mean for it to be at most 2? Well, you colored some set of vertices red and some set of vertices blue, and then the fact that the vertices edges have to have distinctly colored endpoints means all the edges have to go from a red set to the blue set. So it means your graph is bipartite. And so actually we know how to tell if, in this case, if chi of g is greater than 2, because that means that you found an odd cycle. If your graph has an odd cycle, you can't color in fewer than 2 colors because your graph is not bipartite. But there is no similar type of theorem for 3, unfortunately. However, it is known that if you have a planar graph, the chromatic number is at most 4. This proof is very hard. It actually requires a computer to do the proof. There's no human-readable proof known, but it's known 4 colors suffice to color a planar graph. But in general, it's very hard to figure out upper bounds and lower bounds. So we will discuss the trivial lower bounds that are known. One lower bound is that the chromatic number is at least the clique number, where we call the clique number is the size of the largest clique in the graph. So in our committees, we had a clique of size 4 here. And so, in other words, we had 4 vertices that were all friends. And so this told us that the clique number was 4, and this gave us the lower bound for a chromatic number. However, this lower bound isn't always good. For instance, consider this 5 cycle. The clique number is 2, given by any one of these edges. If you take any 3 vertices, one of the 2 edges in the one pair of the vertices doesn't have an edge, so it's not a 3 clique, and so the clique number is 2. But the chromatic number is 3 because this is a odd cycle. You know, if I color alternating red and blue, as most of you saw when you did the homework problem on this section, you run into a problem that this last vertex can't be colored red or blue, so you need a 3rd color. And so you can't color this in fewer than 3 colors. The chromatic number is in fact 3. And yes, you can prove that you pick any number for the clique number, there exists a graph with that clique number and a significantly larger chromatic number. And so, in general, this bound is very bad. We'll also discuss the trivial upper bound. We will improve it in the next lecture. The trivial upper bound is that the chromatic number is at most the max degree plus 1, where we call the max degree is the largest degree of all the vertices. So here the max degree is 4 because this has degree 3, 3, 3, and 3. And this vertex is degree 4. And the idea is to color the large degree vertices last. So you order the vertices in increasing order by degree and color in that order. And so let's give an ordering, say 1, 2, 3, 4, and then 5 on the inside. And then you start using the procedure I used before. Just color with the first available color. So let's say red. And then 2 is attached to a red vertex, so it needs a different color, say blue. And then we see 3 is attached to only a blue vertex, so we can actually color 3 red. And 4 is attached to only red vertices, so we can color it blue. And that leaves us with green on the inside. So in this case, we only needed 3 colors. But in general, you end up needing delta of g plus 1, because what ends up happening is that in the worst case scenario, say delta g is 3, you might have every neighbor having a distinct color. And so then you need an extra color for that vertex. And that's the reason why this bound works, is this algorithm is always guaranteed. It might allow you to use fewer colors, but in the worst case scenario, it's going to use this many colors, because in the worst case scenario, the last vertex, all of its neighbors have distinct colors. But if you have delta G plus 1 colors available, there's one color left over. So you're always guaranteed to color your graph. However, it's worth noting in general this bound could be very, very bad. For instance, you can actually create bipartite graphs with arbitrarily large degree, but bipartite graphs only require 2 colors. So we'll find some slight improvements, but in general, getting much better than this is actually really hard.